Hello everyone, this is a demo video for Lab 9 and we are team number 10 and in this lab we will cooperate with team number 2 and design a router and so in this lab, we team number 10, we design the CPU, ARM CPU for the whole system, and team number 10, they are responsible for the GPU design. So here we briefly introduce our work. It's a very classical five-stage pipeline and nothing very special here since we already introduced it in the last demo video. So we can see that this is we have a 5-stage. And the first stage is for the extraction fetch, and we just deal with the PC counter and some register here. And in the next stage, we read from the register. This is also a very important part. And in the next stage is the EX stage. This is also a very important stage. But we need to know that in the EX stage, we don't have bflow 16. In Lab 9, we design a GPU and a CPU and combine them together. And in the GPU part, we have bflow 16 and vector adder, but in ARM pipeline, we don't have this type of system. So a very classical 5-stage pipeline, and here is a memory stage. And the write back stage. Nothing very special here. So I think we introduced it in the last demo video, so we don't need to prove anything here. So let's look at our teammates' work. Their work is design a GPU. To be honest, I think their design is better than ours. I will tell you why I say that in the next step. So we can tell the difference. So their work is a little bit different from us. They have a specific unit, a module. Is a tensor unit. In our design, the vector adder and the subtractor, we just combine them into ALU stage. But the team number 10, they have a very special unit, and they combine the vector adder, subtractor, and the before 16 operation together. So this is their design. In this part is a little bit similar. We just divide 64-bit data into 4 parts and combine them together in this stage. So I think the first big difference is we don't have we combine the vector adder and the subtractor into ALU, but team number 2 they just do these two operations in parallel, and we can see the second big difference is that you can see their stage. As I said in last demo video, our GPU is based on a 5-stage pipeline CPU architecture, and we just move the original EX stage, and we add a lot of unit in the EX stage and divide them into 3 stages. Because before 16 adder and the subtractor and the multiplier is very complex, so we cannot do operation before 16th operation during one clock. So it will create a very long critical path. So we in our own design we divide the before 16 operation into 3 stages, and the adder and the multiplier they just do a little bit work in one stage and combine them into the EX3, and they have a multiplexer to choose the result. So everything is in parallel. But in here, in team number 2's work, they divide before 16 into 2 stage. So I think this is a little bit different from us. And of course, they reduce the stage number, so it is what I say that they are do a little bit better than us. So they do the multiply in the stage 1 and do addition in stage number 2. And what we do is do these two in parallel. So in the GPU lab, we just consider we are worried about the critical path, so we didn't try more choice. So we divide the EX state into 3 parts, and we never think that we can reduce the stage number. So we can see that it's very interesting is although we have two a very different point. Team number two also choose a similar architecture. Um, they also choose the five-stage pipeline architecture as a backbone. So IF stage, ID stage, and the write back and the memory stage is almost the same. And the EX stage is divided into two parts. So mm, I think uh, in this part we successfully combined the team number two's work into our own design. So I think I include important information in lab 9, and our teammate will introduce more detail in the next step. Thank you very much.
Hi, this is the demo for E533 Lab 9. And we are Team 10 and Team 2 to build a heterogeneous network processor on a single NetFPGA board. The system integrates two independently developed processors, an ARM CPU pipeline that we built in team2&10, and a programmable FBF load 16 GPU tensor core designed by Team 2. Both runs simultaneously on the same chip, sharing memory and controlled through the NetFPGA network register interface. Here is our GitHub repository. All source code, reports, and the toolchain scripts are committed here with daily updates. And here is I will show you our system hierarchy. Um, at the top is top the Lab 8 NetFPGA integration module, which we kept unchanged. It connected to a 256-word shared VRAM, the ARM CPU wrapper, and the GPU wrapper. Um, The ARM core is a 4-thread in-order pipeline. All hardware threads share the same pipeline stages with zero context switch overhead, which completely hides data hazard between instructions of the same thread. The GPU is a programmable processor with a custom BF load 16 ISA to design the original 5-stage pipeline and all the BF 16 arithmetic modules. For Lab 9, we redesigned the GPU control path into a 7-stage multi-cycle FSM to fit in the device resource limit. And now I will show you what exactly the GPU runs. The GPU executes a 6 instruction BF16 FMA kernel. This kernel was originally written as a CUDA program compiled with real VCC31 VCC and converted to our custom GPU ISA using Team2's toolchain. The machine code is loaded as static ROM in a bit file. Now, let's run the hardware demo. We are connected to the NetFPGA test board. And wait, first we need to download our bit file. And sorry, I forgot to not let me start it. And let's run the test. I will, we have already uploaded our test script and run it. First, in phase one, reset the script, reset the system, and set clock mode to enable VRAM access. And in phase two, write test packet into 5 VRAM. The script writes the ARM header data to VRAM worth 6 and 7. And BF load 16 input vector to VRAM worth 0, 1, and 2. Each write goes through 5 arrays writes, address data high and data low, and toggling bit 8 of W data control to trigger the write. Phase 3. To start alarm, CMD bit 3 edge trigger arm start. The arm copies VRAM worth 6 to 12 into its internal data memory, runs the sort kernel, adding 1 to each 32-bit field, and then copy result back. We wait 2 seconds for the pipeline to complete. Phase 4, verify ARM result. Read back VRAM word 6 and 7. Each 32-bit file should be incremented by 1. Phase 5, let's we verify the GPU vector readback. Confirm the input vector are still in VRAM correctly before starting the GPU. And phase 6, we start GPU and verify the result. CMD bit for the GPU start. The GPU runs the 6th instruction kernel. You can see a result. Our test script are all passed. Okay, that's all for our demo. To summarize, Lab 9 is about merging two independently developed processors onto the same FPGA and making them work together. Team 2 designed the GPU pipeline and BF16 arithmetic from scratch, wrote the CUDA to GPU architecture chain, and built the initial NetFPGA interface adapter. Team 10 redesigned the GPU control path to fit the device fixed pipeline timing for VRAM-based register file and debug the three separate hardware issues: register map, VRAM addressing, and the VRAM read latency bug that was invisible in the simulation but caused wrong result on hardware. Thanks for watching.